Hello, dear audience. I am Tongtong Wang, and I'm from the Norwegian University of Science and Technology. It's an honor to have the opportunity to present my work at this conference, but because of the COVID situation, I have to present in this way, and hope it works fine for you. The topic today is physics-informed data-driven approach for ship docking prediction. Today's talk is organized in this way. The general background of the work will be briefly introduced, and then I'll move on to highlight the motivation and the objective for this work. After that, the detailed methodology and the validation experiment will be explained. Finally, I'll end with the conclusions and discussions. It will take about 12 minutes to cover these issues. First of all, let's go through the research background. As we know, the maritime industry is stepping into the digitalization, and it has become a key enabler for making the maritime industries more efficient and innovative for the future operations. The digital twins are emerging as the most promising enabling technology for realizing high-level automation in ship design and operation. The twin shape is introduced as a virtual representation of a physical asset enabled through the data and simulator for real-time prediction, optimization, and control. It is characterized by the high fidelity because it mimics its physics counterparts. As we know, the model-based method is classic and solid, and the physics models they are derived from the dynamic principles created based on the rich knowledge and deep understanding of the system. As a result, a deterministic model is postulated. However, in many cases, the model-based approaches are not always prioritized because of their limitations. So naturally, the ship modeling process initiates from the understanding of the ship system. To capture the different hydrodynamic effects, many models are proposed, each with their own assumptions and scope. Therefore, the uncertainties and the simplifications are unavoidable. Another limitation is associated with the parameter uncertainty. A lot of efforts and time are needed to estimate the hydrodynamic parameters, but still facing a lot of challenging issues such as the multi-collinearity problem. It is not easy to build an accurate ship model. It requires a lot of expertise and extensive research to establish a physics-based model. Well, the data-driven approaches, they're modeling the ship system in a totally different way. It simulates the dependence between the input and output variables implicitly. They can represent the system as close as to reality if enough data are supplied. So they outperforms the physics-based models in accuracy, especially for the complex nonlinear systems. And a lot of advanced approaches are being increasingly used in the maritime field to support the decision-making process. Although the data-driven approaches works quite well in many cases, it does not practically a perfect manner because the performance is quite restricted to the training data quantity and quality. And a lot of machine learning approaches, they are often processed as the black boxes whose inner process are difficult to interpret. So it leads to the difficulty of tracing the origins of errors through the model. And on the other hand, they abandon the well-understood physics, which means that the models, they are learning the experiences that are exactly included in the training datasets, but exclude the physics information that may be useful when the model is exposed to the new data or new scenario. As we clarify these two modeling approaches and the gap between them, we are expecting to see a better performance if the stability of the prior knowledge and the flexibility of the data are collaborated together. And more practically, there are always cases where the partial but not complete information is known about the system. And we hope that physics data hybrid methods each could offer a new insight into that process. In the shape motion prediction application, three models are constructed, a physics-based derived on the hydrodynamic properties, and a data-driven one without the prior knowledge, and lastly, a physics and data hybrid model. And we mainly focus on developing the hybrid model, and a further comparison among these three models will be covered. The methodology we propose incorporates the approximate dynamics into a data-driven calibrator, which leads to a representative model of the target shape that can be used for the maneuvering prediction. In this method, we take the research vessel Gunnerus as the test bed. The hydrodynamic model of this shape is existing and validated, but it is simplified. And meanwhile, the real shape operation data is sampled on board. The simple shape model it provides an approximate dynamics, and the prior knowledge is carried forward into the network as the input, and the informed neural network calibrates the bias between the model outputs and the real states in principle. Here we come to the reference shape dynamic model, and this equation shows it supplies the prior information about this shape. Two assumptions are clarified here. Firstly, the forces due to the waves are not constituted, and second, the force due to the ocean current are not included either. So the shape velocity relative to the water will be replaced by the shape velocity. And in the data-driven calibrator, the input and output variables, they are formulated here, and a feed-forward neural network is used to learn the map from the model prediction to the real states. And the training performance is evaluated by the mean square error. To learn a purely data-driven predictor, we use the long short-term memory network in this study because of its advantages in dealing with the time series data, and a single-step predictor in trained on the real-life docking data. The docking data is sampled on board the research vessel Gunnerus, and the measurements it contains the ship's GPS signal, 6 degrees of freedom displacement and velocities, wind direction and speed measurements, so as well the thruster feedbacks. And a docking operation dataset of a 1-year time period was selected. A conversion from the latitude and longitude in the Earth-centered Earth-fixed frame to the northeast frame is implemented on the dataset as shown in this left figure. And the sampling frequency of all the variables is 1 Hz, and in total 70 complete operations. Each contains 1,000 seconds in length were recorded. For the physics-based model, only the hydrodynamic properties are involved and there is no data participated. For the model and data hybrid approach, 6 docking operations data were used for training the neural network. And for the data-driven model without the prior knowledge, the LSTM is trained on 50 operations data. The 3 models, they are verified on the same test scenario as shown in this left picture, and the mean thruster feedbacks and speeds, they were recorded and as the right figure shows at the same time. It is observed that the 2 mean thrusters, they are controlled in a separate way. And the predicted trajectories of the 3 models in the test scenario, they are visualized in this left picture. According to the control signal, there are 2 stages in this process. before and after the port side thruster turns. Therefore, two details they are displayed in the right, where the right circle represents the ship's position, where the forecasting is initiated, and the three predictions are indicated in three colors. It is saying that the hybrid model predicts the most accurately in both the command profiles. A prediction error comparison is conducted and shown in this left figure. The average Euclidean distance is introduced to evaluate the errors. And it is observed that the prediction accuracy is strongly related to the ship's speed. Generally, the hybrid model considerably reduces the prediction errors compared to the hydrodynamic and LSTM model. In terms of efficiency, these results show that the hybrid model can achieve a good accuracy with limited data and a simpler network structure, which spares a lot of efforts and computational consumption than building everything from scratch like the LSTM network without prior knowledge. In this paper, for the cases where partial but not complete information is known, the physics-based model is therefore not qualified to represent the system. But at the same time, limited observation data is available. We propose a physics and data hybrid modeling approach to enhance the model quantity. The prior knowledge leveraged by the rough shape model is carried forward into the neural network as informative inputs, and the informed neural network calibrates the bias between the model outputs and the real states in principle. The proposed approach is validated on the real shape docking operation of a research vessel. Results have shown that compared to the purely hydrodynamic one, the hybrid model outperforms in accuracy. And compared to the data-driven model, the hybrid model could be achieved with fewer data and faster computation. Here is the references we used in this presentation. And thanks for your attention. Any questions and comments are welcome.